So now let's address the B-band luminosity issue that I talked about before. Here is a sample of the data. This one in particular is looking at the asymmetry of rotation curves. There's the paper where you can see this. You'll note that what I do is I look for data that exists and I plot all the galaxies that I find. Now, each of these points is basically a luminosity parameter versus the asymmetry as noted. And you can see the data points. I've drawn lines through several. You notice these are grouped as on one line. These then come as another line. The difference between these lines is approximately the difference between the slopes of these lines is approximately 2. And that, I think, is very significant. Now, competing people, that is to say the standard practice in the industry, will take a look at a graph like this, and they'll plot some line that comes someplace like that. Okay? Many in the physics community will take a look at this kind of data, and they'll plot a line going someplace out like that. And they accept then a large error. This is approximately 30% error. They accept a large error. And when they take a look at these kind of things, they will say, whoops, there's something wrong with these galaxies. Therefore, they will select these galaxies out of their sample. And then they accept only these galaxies in their sample. And that's roughly 80% of the galaxies. Well, 80% is pretty good, and most of them go along with this. I don't do that. I'm looking at all the data, and all the data is going to include these very funny galaxies that seem to be standalone galaxies. And we note that the relationship between this one and these down here. So what I'm detecting here is a very interesting, to me anyway, in that between these lines is a gap. The galaxies don't appear in here. You see, there's nothing here. If it was evenly distributed, or let's say randomly distributed, you would expect to see some galaxies in where we have gaps. So why do we have these lines whose slope differs by about a factor of 2? That becomes a problem to be solved. But having different types of galaxies is not unusual in the universe. Here we see what is known as a Hubble classification scheme, where you got elliptical galaxies and then spiral galaxies all out here. Some of the spirals have bars, and that's these things, where you note that that's the bar, that's the B here, and others don't. Now, it's kind of interesting that there are 6 of them and 6 of my lines, but I looked for a correlation here between this morphology type and my lines and didn't find it. But there have been some interesting things that come up, which we'll get into later on. Rotation curves. The discrepancy between the Newtonian and general relativity mass and star and gas kinematics in spiral galaxies is well established, and they're called rotation curves. There are some issues here which I'd like to address. The focus has been on flat rotation curves in the outer part of some spiral galaxies. But rising and falling rotation curves also exist, and these things are falsifiers of dark matter, falsifiers of the MOG, modified gravity, and the MOND. Now, the general rotation curve is generally not understood, but in general, close to the center of spiral galaxies, the rotation of stars and all is up into the thousands of kilometers a second. Okay, this is the data of the S stars in our galaxy, thousands of kilometers a second. And this is all within, the center of the galaxy being within 12 AU of the Sagittarius star position. But the other thing you realize is the decline from that thousands as you go out in terms of AU is very rapid, and it's Keplerian, meaning it obeys Newton's law. But then a funny thing happens. Someplace very close to the center in the bulge, the rotation velocity becomes very, very low. Some say even zero. That is to say, it's as if there is no mass effect beyond this point outward. It's zero. But that's not what we see. So here you have some matter beyond this 0 point, and the rotation velocity is increasing. But can't be due to any mass here in the middle, because this is zero. This then is a problem. Ouch. Ouch. Ooh. The problem is termed as why are outer galaxy parameters, meaning parameters out here, related to inner galaxy parameters, like the mass of the central massive object. And okay, if this creates a problem, the problem is it has been noted that outer galaxy parameters out here are related to inner galaxy parameters such as the mass in the central area of the galaxy. But with this being very close to zero here, that relation should not exist in normal Newtonian or general relativistic equations. Now, after that means there's mass accumulating here at this point, and it's increasing, and this then is due to the mass here. What happens out here is due to the mass in this zone and not to anything in the central area of the galaxy. And as you can point, as I diagrammed here, the rotation curve can be more or less flat, which most galaxies are. There's a significant portion of them, that have a rising rotation curve, and very limited, I might add, and some that are actually falling. Just as a note, rotation curves usually measured along the major axis from our viewpoint. Stars near the center have rotation velocity that's very high. Here's an example of 4321, and this is the paper you see it is. And here we plot rotation velocity versus the distance from the center, and we've kind of ignored the very center. This is from the zero line here for the filled diamonds, which is HI, and the filled diamonds extend out beyond the luminous range. And you see it's anything but smooth going out. But anyway, here's the same galaxy, same plot, only now we're looking at H alpha line. And the H alpha line is essentially ionized hydrogen. That means these are luminous stars you may see, whereas beyond this zone here, this is molecular hydrogen, and you generally don't see it. It just goes on. And this is the zone that is considered the flat zone out in here. In here is the rising zone, and you see the rising is anything but uniform. Asymmetry. This is kind of busy, but you have to do something. This comes from this paper, and we have a little problem of just exactly what do you mean by asymmetry. What the STOE does, here's one side of the galaxy and the other side from the center, and you'll notice that the two have a slightly different rotation difference in the rotation curve. That is the STOE asymmetry. Now, other people don't look at this as being asymmetric. They draw it simply as one line, and therefore they ignore the asymmetry. But the truth is that most galaxies have some amount of asymmetry as measured like that. For 20 or 30 years, there were papers being published about asymmetry, and nobody come up with a good model for what asymmetry was or how it was caused, and therefore they just seem to have stopped looking. Well, asymmetry is part of the data, and we do have to look at it. The evidence suggests that cluster environment affects the RC is contradictory. The evidence that cluster environment affects the rotation curve is somewhat contradictory. This is because it typically follows the ionized hydrogen rather than the outer galaxy molecular gas. Ionized hydrogen being stars, and stars kind of stop about halfway out of most galaxies, most spiral galaxies. And the molecular hydrogen then becomes much more sensitive to environmental effects than our stars that are fairly far inside galaxies. Also, in the STOE, asymmetries in other people's, also, asymmetries in the side-to-side variation in the outer parts are nearly all galaxies, but are usually ignored. They are averaged. Many characteristics of RCs are unexplained. Many falsify current models, including infall models required by the Big Bang model. Others have rising rotation curves from the minimum outward, implies a slowly increasing amount of mass from near zero is affecting the RC. That is, as if there is no mass effect of the central region around the supermassive object in the center of the galaxy. Why is the disk centered around the supermassive black hole when the calculations show no mass effect of the supermassive black hole on the disk? Or what is the relation of the central mass to the disk parameters where no relation should exist? Other discrepancies with the accepted model. This is an example here where this doesn't look like a nice rounded smooth, right? It has very sharp delineation points, such as right there and right there. You see, so it looks like a piecewise linear fit to this data is a better fit than some kind of a nice smooth curve. So the STOE has three forces acting on matter outside of the center region. One is the gravity of the inward mass. Now, this is not the bulge mass near the central mass of black hole. This is the mass outward from where the rotation curve reaches a minima near zero. The effect of the source strength is still there because the plenum is still acting, and therefore it's ejecting, which is what the negative sign here is all about. Plus an effect from nearby galaxies. In the STOE analysis, we take a look at the difference in rotation velocity at some distance along the major axis. This is a redefinition of what asymmetry means. Most people take asymmetry to be difference of radius to get to a given rotation velocity. So this is unique to the STOE. My sample, when I did the work, was 105 spiral galaxies, which is all for which RCs were found. There was no selection bias here. If it had an RC published, I went with it. 16 of these galaxies had Cepheid-Star distance calculation, which we consider very, very accurate. 49 of the sample have published asymmetric RCs. Many others probably had it, but I couldn't find the data. Here then are the 16 that have the good distance, the Cepheid distances relations. You'll notice this one, and this one all have rising rotation curves. These things are falsifiers of dark matter. Some others have some unique structure, like here, in the outer part of the rotation curve, which is, again, molecular hydrogen, not stars. And these are then very sensitive to what other galaxies are doing. Note the uncertainty here. And you remember my little lecture about doing the data, these are the equations. There's a B band luminosity. This B is going to be approximately 2 for these kinds of equations. And you note that if you don't take account of the asymmetry, you end up with something around 10 to 20% uncertainty. Okay, but that's still good because when you take effect of all those so-called outliers, if you just want to form one line rather than this many factors, you end up with 30% uncertainty. and having many galaxies ignored. However, when you do the same thing and you include the asymmetry in the RCs, and here we're looking at these things with the asymmetry, this is the asymmetry involved. There's the effect of the neighboring galaxy, and you'll notice that suddenly these uncertainties really decline. So there's no reason why you should have very high inaccuracies, except for selection bias and because asymmetry being improperly accounted for. Okay, so here's the issue of the inner rotation curve dropping down to zero in a purely Keplerian fashion. The galaxy's central mass and central velocity dispersion are the two measures, and B-band luminosity correlation in the outer galaxy. Many researchers have noted this correlation, but is generally unexplained in the standard model. The STOE suggests the amount of matter and therefore structure is derived from Sorth and Sink strength and not from the direct attraction of the central mass. And here's the central velocity dispersion, and we got a nice relationship going here. This is the central mass. A prediction. Here, what we're doing back in 2003, 2005, we were suggesting that neighboring galaxies influence rotation curves. There's the paper. Generally, this has been ignored throughout the years. However, starting in around 2017, some papers began to suggest that the correlation of spiral galaxies tilt related to neighbor galaxies. Well, this is kind of a prediction, meaning the STOE has always suggested that neighbor galaxies do influence other galaxies. So, you know. The STOE model is an alternative to and is more complete than relativity, the Big Bang model, and the QSSC model. It is Machian. It explains many problem observations and includes the small in the first video. The unexplained blue shift in the radio signal from the Pioneer spacecraft is well established. The Pioneer anomaly is experimentally observed as the residue of a frequency shift after the Doppler shift effect is subtracted by expressed as an apparent acceleration. This is based on a notion that the Doppler shift applies to the residue. This assumption is unsupported. Another unsupported assumption is that the blue shift is sun-directed. The Pioneer anomaly could be an effect other than a real acceleration, such as a time acceleration or an effect of an unmodeled effect on the radio signals. Although unlikely, a currently unknown systematics effect is not entirely ruled out. An obstacle to a new gravitational physics explanation of the Pioneer anomaly is that a modification of gravity large enough to explain the Pioneer anomaly is in contradiction to the planetary ephemeris unless the equivalence principle is violated.
The accepted opinion is that cosmic dynamics, according to general relativity, has far too little influence in galaxies to be measurable, and that the expansion of the universe is essentially negligible for scales up to galactic clusters. Further, the expansion of the universe indicated by redshift has a sign opposite to the acceleration. Data for the existence of the acceleration from Galileo, Ulysses, Voyager, and Cassini spacecraft are suggestive, but inconclusive. The currently accepted explanation is that thermal radiation from the spacecraft exerts a sunward recoil force. The problem: there are several other characteristics of the data that are ignored. The Scalar Theory of Everything model for the Pioneer anomaly is that matter causes a static warp in the plenum that causes the effect on the signal. The gravitational attraction, the equivalence principle, and the planetary ephemeris remain as described in general relativity. Therefore, the equation used to calculate the redshift for galaxies applies, where the matter acts like sinks in the equation and the observed blue shift is the negative of the galaxy redshift. You can see my video about redshift. The amount of warp, rho, at a point in space was posited to be equal to the gravitational constant times the mass of a body divided by the distance to the point. And to get rho at a given point, you sum over all masses. The equation for the calculated redshift is as in the galaxy redshift. The terms are defined in the redshift video except for DL is twice the distance, and two of the terms are zero because the distance we're concerned about here is small relative to galaxy distances. This is the data for Pioneer 10. The diamonds are the data, which are here, here, and here. The squares are calculated, and you can see it's a pretty good fit. The X's here are calculated for dates 10 days from the date of the data, and that's because the duration of taking a data point has been about 10 days. This is for the Pioneer 11 spacecraft. This point here is the Saturn encounter, and you'll note that before the Saturn encounter there looked like there could have been a redshift here, but a very slight blue shift at least. Then the Saturn encounter had a very large error associated with it, and these are two things that are unexplained by the current model. Because the value of the acceleration depends on the closeness of matter to the line of sight, a change over 10 days or longer is due to long integration times. The correlation coefficient we saw in these two previous graphs is about 0.93. The following are the other observations of the Pioneer anomaly that are poorly explained by other models. First is the annual periodicity. Anderson noted an annual sinusoidal variation in residue of the data. Sinusoidal means a circular motion around some point at a constant radius. Such a motion is the apparent motion of the Sun around the Earth. There's a sine term, is the distance of the Sun to the line of sight. Line of sight to the spacecraft, the angle we're concerned about is Sun, Earth, spacecraft, and this is then the sine of that angle. If the angle Sun is large, in this case where the Sun is on the other side of the Earth from the spacecraft, then we get a nice smooth 1/r kind of distribution. If the angle to the Sun is small, then we have the effect of the Sun on the electromagnetic signal. You will note this is similar to the discrete redshift. The same applies to the sidereal periodic motion. That is to say, the send and receive station of the signal is on the surface of the Earth, and there's a constant radius between the center of the Earth and the radio station. The difference in the acceleration between spacecraft is because the outer planets are on the opposite side of the Sun for P10. The effect of the planets on the acceleration of P10 is less than on P11. However, as d of the P11 increases, the planet's effect approaches a constant value. The STOE expects the galaxy mass to have a small difference between the spacecraft caused by their different travel directions. The orbit of P10 is closer to the Sun's Sagittarius A axis than P11, and the distance of P10 is greater than the distance of P11 because it's been in space longer. Now, the Sagittarius A is where we think the source in our galaxy is located. However, the effect here is within uncertainty levels. The difference between the two programs' methods for analyzing data are different in the early stages of the Pioneer 10 and closer in agreement at the later stages of the Pioneer 10. The varying acceleration may explain the difference. The AP is not constant, as one of the programs assumed. The slow decline in the acceleration, the radio signal measurements are from and to the Earth. At small distance, the relative effect of the Sun-Earth distance is larger than at farther distance. As d increases, the solar system effect appears to approach a single mass located at the very center of the solar system. Therefore, the acceleration declines and approaches a constant value dictated by the rho being inversely proportional to the negative of the distance. However, the STOE expects that at much greater distance, the effect of the galaxy mass will increase to cause a difference in the AP values between the spacecraft. This plot shows the acceleration varies widely over a period of hours closest approach of P11 to Saturn. The negative acceleration calculation is a redshift, as seen in the previous figure. Data at the beginning of the encounter has a near zero blue shift. A large uncertainty in the second P11 data point is the Saturn encounter. This data point extends over a relatively long time, some 50 days. The rapidly varying acceleration in the previous slide is consistent with the uncertainty. You'll notice the angle of the Sun is nearly on the other side of the Earth from the spacecraft, and so it doesn't play much of a role. The cosmological connection. Here's a plot that we had in the redshift video, where we have distance versus the X factor, and we see something very similar to what we saw in the redshift video, except that the sign is different. There's the formula for the graph like we did before. This has a 95% correlation coefficient, and we calculate H0 to be 106. The Pioneer anomaly and the redshift of cosmology are the result of the same rho effect on light. In the cosmological redshift calculation, the Z follows the Hubble law if rho is inversely proportional to the radius. In the gravity well, the redshift follows a negative Hubble law. That is to say, rho is inversely proportional to the negative of the radius. Hence, the negative of the galaxy redshift cosmological constant. Galaxy redshift and discrete redshift are the same phenomena as the Pioneer anomaly. Predictions of the STOE in 2006 concerning the Pioneer anomaly that no other model predicted have been published later in 2009 and 2011, and these are the two papers it was published in. Because the Pioneer 11 data before the Saturn encounter was near zero, the accepted explanation was there was no Pioneer anomaly before Saturn. The data before the flyby encounters were insufficient to detect the Pioneer anomaly. That's what the paper showed. The STOE requires that to be the case rather than that there was no Pioneer anomaly before the Saturn encounter. The Earth direction is marginally preferred. Other models, including the thermal recoil model, consider the Pioneer anomaly to be sun-directed. Earth-directed implies a signal effect, which is what the STOE has. We quote, "The data favor a temporarily decaying anomalous acceleration. The decline is exponential according to the STOE, except when the signal passes near a large mass, such as during flyby maneuvers." The STOE model, all the data of the Pioneer anomaly, is not just the one type of data. The STOE model has made predictions that have been discovered later. The STOE model is more universal because the physics is the same as for galaxy redshift.
Now that the transparent mask project and the special relativity project are done, except for writing the papers, it's time to consider what's next in the STOE. This paper will show you about where we are, and many of the projects we've had in the past have threads which could lead to more interesting stuff, and those are all possible projects for what's next. The STOE is causative and Machian model. It reduces to general relativity and quantum mechanics, which makes it a theory of everything, and explains many problematic observations that both general relativity and quantum mechanics have. It has made predictions, which have later been found to be true. The STOE rejects, by experiment, Maxwell's equations, wave models of light, and the idea of the Lagrangian and the Hamiltonian mechanics, which do not have dissipative characteristics. One thing we can look at is the constants of the universe. As a result of negative feedback loops, the problem here is identifying what the feedback loop is. This was done for the cosmic microwave background temperature, which is a typical temperature feedback loop in that paper. Looking at the gravitational constant is another thing we can look at. The STOE uses three types of mass, which comes from Newtonian physics. The weight, which in the STOE is a plenum gradient onto the surface area of a hod. The inertial mass, which is in the plenum, so it supports wave actions. And the gravitational mass, which is what hods cause in the plenum wave. This works well for photon simulation, which was done. So gravitational constant changes with body structure and perhaps with plenum level. The strong equivalence principle here is rejected, but the weak one is accepted. Entropy and the arrow of time is another thing I've been thinking about for quite a while, and it's still quite a problem. It occupies about a foot-high paper on my desk that I should look at. Universe entropy must include a dissipative or friction term. The standard models are Lagrangian and Hamiltonian, which do not. Therefore, the current universe model of entropy is not accepted. Causality of changing events implies energy input or output. If output, then the arrow of time from source to sink, as you see in the galaxy structure, suggests a constant universe entropy, rather than entropy is always increasing, as this current model suggests. We could also apply the redshift equation to the Pound-Reeve experiment. Z has already been applied to the Pioneer anomaly, all 10 of the anomalies, whereas the standard model only applies to one of the anomalies, which means it's not that good of a model. This model made predictions which were later confirmed to be true. We could apply the photon simulation to reflection, refraction, and the quantum eraser experiments. This has several problems associated with it, but maybe what we could do is redo with the length of the plenum wave as a function of the number of hods in the photon, rather than using the model of linear dipole antennas. Now, Bohm has suggested a point particle, and the STOE doesn't accept point particles, it accepts some extended space. And we could do this rather than indirectly, as the photon simulation currently suggests, as a body with volume rather than a point. I would note something of interest here, and that is these Walker experiments, which use only one drop to make waves, which then cause diffraction when going through a slit. This is why we might look at the length of the plenum wave concerning with the mass of the photons. It may be easier with this to consider reflection. We could apply the rotation curve equation to spiral galaxy orientations. Recently, some papers over the last 5 years or so have noted correlation of spiral galaxy disk orientation in space being somewhat related to their neighbor's position. Now, the asymmetry of the rotation curve was considered, and it considered these neighbor galaxies, and so this spiral galaxy rotation orientation may be considered a prediction of the standard scalar model. This is the issue that we have. Currently, where here you have rotation velocity squared compared to all these galaxies and versus B-band luminosity. Now, you'll note that there seems to be several relations. The slope of each of these lines is twice the previous line. And this area in between the lines is actually a void area. Now, the slope of the lines differ by approximately 2, and statistically, the form is significant by rejection of the null hypothesis that the data points are random. What galaxy characteristic does the B-band luminosity depend? That's the problem. If we could find that, maybe we could have just one nice line in the previous graph. That would also apply for central mass, which was another paper. Another effect of the source at the center of Milky Way we could look for. We've already applied it to RCs, as we said. Planet 9, there's 2 papers on that. Mercury and other planet orbits seem to have some relation to the source in our Milky Way. And of course, the source in our Milky Way was part of the Pioneer Anomaly paper. We could expand the idea of structure of particles being like disk magnets to quarks. What that structure appears to be that it's going to be like electrons being held together by photons, is what it looks like. But, I've yet to come up with a structure. I could form a ball of disk magnets, which would be a nucleon, such as a proton and neutron, and do collision experiments using a ball disk magnets didn't work, so perhaps disk magnets would work. We could look for a method to measure the speed of the magnetic force. Now, in the STOE, that would be the permanent magnet force, not the electromagnetic force. The STOE found that these 2 kinds of magnetic forces of Maxwell's equations are different. Now, one of them, the electromagnetic force, appears to be producing the electromagnetic waves which travel at the speed of light, and that is the speed of hods. DeSangro and others looked at the speed of a Coulomb force and found it to be many times the speed of light, and the STOE would suspect that the speed of the permanent magnetic force would be a plenum thing, and therefore would have a very high speed relative to the speed of light. The trouble is finding a way to measure that. Consciousness is something I think about for a while, but I think before the industry can go forward, it has to define just exactly what consciousness is. And that, of course, is lacking. in today's discussions. STOE views life and societies as part of our universe. Therefore, the basic postulates of physics should also apply to life and societies. And I looked at that in this paper. But of course, the reverse is also true. That is to say, the characteristics of life and should also apply in physics. That is to say, life expands by means of giving birth. And so there must be a form of birth in physics, which the STOE looks at. In the STOE, I looked at emergent characteristics, and these are a little different than what most people mean by emergence. But if we apply consciousness to the STOE, it could be an emergent characteristic, which means human and animal and plant emergent characteristics, or it could be present in all objects in the universe, such as rocks. Now, this has once been suggested by ancient Greek philosophers when they noted that objects, meaning rocks, tend to find their natural place in the universe. That means they have to know where their natural place is. And also in the view of where Hades is compared to heaven, meaning heaven is up and Hades is down into earth, because the earth was considered at the center of the universe, at the center, but not the center, because all earth is a gravitron. Oh, well, enough of that. Current approaches tend to view the brain as a digital computer for processing and collating information. Now, the STOE approach might be very different from that. It could view the brain as an analog mechanism. Therefore, it can have a great many more levels per given unit of time, which means a great many more digital processing rates. We could also, something I've been working on for quite a while, is to consider a third U.S. Constitution. Humanity seems to lack sufficient understanding to form a government with long-term survival. Most types of government organization that we know of have failed in the past, except maybe perhaps for the U.S. one, and yet that seems to be in trouble. The best that these organizations have done, such as the Roman Empire, is to transition from one form to another that collapses. That is to say, the nation collapses to a state, such as the Greek city-states, which then collapse to be tribes, etc. And I've written a couple of papers starting to examine this about steering humanity's growth and the growth challenge of the United States. Well, those are the things I'm thinking of for application of the STOE, but of course other possibilities are open also. Throughout this presentation, you will see an IA followed by 4 numbers. This is a link to the website, Intellectual Archive, and these 4 numbers reflect the paper that's on that link. The STOE has some predictions. A model should have predictions for it to be valid, at least explain problem observations while reducing to current successful models. So what we're going to cover here is going to be 5 predictions for sure, 2 that might be predictions, and 1 that seems to be developing over the last few years. Now, prediction means data ahead in time. So you make the prediction, then the observation verifies it. And a second thing is that all other models must fail. I mean, it's not a valid scientific theory if you hold a pen above a desk and you release the pen, that it drops to the desk. Many models suggest this, so that's not really a prediction in the STOE or any other model, because many models suggest this. Some consider a model describing existing data as prediction. I don't. And the prediction must be different from what other models predict and describe, as we said. The STOE model predictions started in 2006, and here's the archive reference. about the Pioneer anomaly. These are the three predictions that the STOE had in its analysis of the Pioneer anomaly. The STOE predicted there was a Pioneer anomaly before the flyby encounters, whereas traditional models held there was no early Pioneer anomaly, that is to say, before the Saturn encounter. The other models had the Pioneer anomaly as being sun-directed. The STOE was the only model at the time, meaning 2005, 2006, was the only model to hold it was Earth-directed. The STOE held a decay in the Pioneer anomaly, whereas other models suggested only a slight temporary decay around the planet encounters. I might also note that the STOE is the only model to describe all 10 of the Pioneer common characteristics that were pointed out by Anderson in 2001. However, these were known, and therefore describing them is not a prediction. Most other models of the Pioneer anomaly only talk about one or at most two of the characteristics, and therefore they fall short. Also, the Pioneer anomaly paper mentioned trans-Neptunian orbits of Pluto, the TNO orbit of Pluto, caused by the galaxy source. Planet 9 data in and around 2013 papers of TNO objects attributed their orbits to a, quote, planet 9, which is directly opposite to the sun from the Earth. Now, this should be reminiscent for the explanation of rotation curves being caused by dark matter, whereas the QSSC and the STOE model attributes it to the source of the stuff of our universe coming out from the center of galaxies, spiral galaxies, and they're caused by sources. The interference of light in the transparent mass experiment was predicted. Indeed, the experiment was constructed to use the effect to examine in the index of refraction in papers. The Hodge apparatus, a single slit with the second mass placed in the diffraction pattern, was used to examine interference effects of objects. The key is the diffraction variance of intensity from the slit in the second mass. The maybe prediction, I started by noticing Maxwell's equations differ from the STOE. The experiment that rejected the Biot-Savart law, there's the reference, was done because the EM radio signals travel at sea, which implies the hods are the elements. However, this seems to conflict with the Biot-Savart law. So the typical experiment was done using a magnet rather than a parallel wire, and the Biot-Savart law, as it's currently stated, was found to be incorrect, experimentally incorrect. The result of this experiment suggested the STOE another experiment on electromagnets. And this is the paper which showed two different types of magnetic field and that the Maxwell's equation should be done. The developing prediction comes from this paper about neighboring galaxies' influence on rotation curves. Recent studies from 2017 and on suggest correlation of spiral galaxies' tilt is related to neighboring galaxies.